Hey guys, so in this section what we're going to do is talk about free body diagrams, and all that is really just a drawing of the scenario with all the forces acting on it, completely free from anything in its surroundings. So you just focus on the object you're interested in and determine from the list of forces we had from the last video what is actually acting on this object. So you can draw the object, draw the vectors with their magnitudes, their directions, label all the forces. And if you have forces in the same plane, like x forces or y forces, what you can do is combine them to find the net resulting force to figure out where this object is going to go. So similar to the bowling ball demonstrations we saw today, let's look at some free body diagrams for those scenarios. So what we have here is scenario 1 from today's examples with the bowling ball. We have the bowling ball here at rest. So I'll mark number 1 so you know which scenario we're looking at. With a bowling ball here at rest, we can identify what forces were acting on the bowling ball at the time. Well, we know that what keeps it on the ground is the force of gravity. We have the floor that's supporting that bowling ball pushing back upwards with a normal force. And since the ball was not falling through the ground or being launched up into the air, what you could say about those two forces is that they're probably balanced. The object is not accelerating up or down, so those two forces must be canceling out. What we also had was a hammer. The hammer was hitting from the back side of the ball forward, so we could say there was an applied force forward on the ball, and that strength didn't have to necessarily be the same as the normal force of gravity, so I'm just going to indicate that with 2 lines to show that that force is different. And that was probably it. I mean, let's assume the floor was pretty smooth, so we don't have to worry about friction at all. There was no ropes or springs involved, so there was no tensions. So out of all the forces we've got, there you go. Looking at the scenario, if I create the motion map, the bowling ball was at rest and started to pick up velocity each second as you hit it. With that being said, that means that there must be an acceleration towards the right. So that acceleration shows that the velocity is changing in the forward direction. And the reason for that has to do with this force. If you look at those 2 up and down forces, we said those balanced. So there's only 1 force left over, so this whole scenario must be an unbalanced scenario. The forces are unbalanced, which caused acceleration. Let's look at scenario 2. In scenario 2, ball's moving in and comes to rest. So it has a high velocity, gets slower and slower until the ball finally stops. Okay. In terms of just a motion map, that means there must be an acceleration against the motion. The acceleration is changing the velocity and decreasing it until it stops. So if I'd identify forces again to make a free body diagram, I'm going to say gravity down, support up. We have a normal force up. And to slow this ball down, we had to hit the ball from the right side to the left, so there was an applied force backwards. Without knowing numbers and just looking at that scenario, I can see that probably the up and down forces again will cancel, leaving just the applied force to act on the ball. So this is another unbalanced situation. So with unbalanced forces, we're seeing acceleration take place. Looking at scenario 4, that was accelerating it to a line, stopping it and turning it back around. Rather than drawing the bowling ball and the ground and all that again, this is more what a free body diagram looks like. There's my bowling ball, and I can identify the forces. So in the beginning, force of gravity acting down, support force upwards, and to make this thing pick up speed, an applied force. That made it pick up speed to the right. The ball started to accelerate, and then to get rid of its speed, we saw you try to hit the ball in a way that the velocity would get lower and lower until it stopped, turned around, and started to head back towards the finish line. If I draw a second free body diagram for this turning point, I can see again gravity down on the ball, support up, and in this case, to slow down the ball, I had to hit it in the opposite direction with an applied force. So my force diagram in both scenarios, whether I'm picking up speed or losing speed, shows unbalanced. So unbalanced forces seem to cause acceleration. And looking at this example, you have someone dunking, so they grabbed onto the hoop and they're pulling down, and let's say that they're just hanging there. The forces could be the force of gravity that would be pulling down on the player, and you've got the springs, the tension in the hoop, whatever you want to call that, pulling back up to hold the player there motionless. In this scenario, I can replace the player with just that box like you see. That dot represents the person. If this person is at rest, they are not accelerating, so I would say these two forces are balanced. With that being said, balanced forces cause no acceleration in a scenario. Let's look at this dog sled. In the dog sled here, they're identifying three forces on the sled. Gravity, keeping it on the ground. We've got support from the ground pushing back up. That's your normal force. And the applied from the dog, whether it's tension, applied, whatever you want to call it. In this scenario, just looking at three forces on the sled, I would call this an unbalanced scenario. Unbalanced, I would expect the dog to accelerate that sled to the right. When we do any of our scenarios, what we want to do is see if our scenarios will obey Newton's first law. And we covered this in projectile motion. And Newton's first law says objects at rest or objects in motion will remain at rest or remain in motion, whatever you were last doing, until there's this outside net force. So from our bowling ball scenarios, what you can see is if we have an unbalance in forces, that object will accelerate towards the unbalance. In player hanging off the hoop example, the forces were balanced. He was at rest, he wanted to remain at rest, and there was no outside influence, outside net influence. He had two forces on them, but those two forces canceled out to zero. So the object will keep doing what it was last doing. And all these will be true in what we call an inertial frame of reference, a frame of reference that follows constant velocity. So either a frame that is at rest or a frame that is constantly moving. The example here, this lady's sitting in a plane and notices the tennis ball move back towards her. So from her point of view, the tennis ball is accelerating, but if you look at it from the ball's point of view, the ball's just wanting to stay at rest, and she is accelerating forward as the plane takes off. So to show some examples here of inertia in motion, you've got this horse being branded, and he's not enjoying that. What I want you to focus on is the guy's feet. So if you focus on this guy's feet down here, he is at rest in the beginning. He brands the horse. The horse does not enjoy it. The force right here is applied to his chest. Watch his feet. His feet are at rest. His feet are still in the frame, and his feet are still there. His chest accelerated. There was an unbalance in forces up on the top of his body, but the bottom of his body wanted to remain at rest. So watch it again fast. Watch his feet at rest and remain there until he has to go catch up with the rest of his body. Poor woman's out here going for a parasail and has a very bad day. So what we can watch if we do this in slow motion is that when the boat takes off, she's not paying attention, and the force is applied to her stomach. So her stomach accelerates, but her head and her feet are remaining at rest. Let's go one more frame ahead. Can I do that? Oh, there they are. Her head and her feet are still in the same spot, so only her stomach was accelerated and her feet and head tried to remain doing what they were last doing. They were obeying Newton's first law. So we can watch it one more time. Watch her head and feet, and they stay put. Watch this video here of an object in motion. The guy was in motion. He wanted to remain in motion, and there must have been some outside net force causing him to accelerate. In this case, the glass. Objects in motion will stay in motion unless acted upon by an outside force. And you can see he quickly gets out of the store. And even your pets are subjected to Newton's first law. The dog was at rest. What happened here? You accelerated. The dog tried to remain at rest, and he tried to stay in the same spot. You feel this every time you hit the gas in your car. You feel like you're being thrown backwards, but it's your body just wanting to stay there. It's the car that takes off and accelerates and forces you to go forward. Or once you're already cruising at 60 miles an hour and you slam the brakes on, everything in the car wants to remain at 60 miles an hour. So it all flies to the front. It's just trying to obey its inertia. According to what we talked about, we have unbalanced forces causing acceleration. A push or pull on an object is your force, and when there is an outside net force, it'll cause changes in velocity. We saw that with the bowling ball. Any of the unbalanced scenarios had a change in the object's speed, or it had a change in the object's direction, like when we made that sharp left. What we can say is that a law of nature that we could follow is that if there's a constant force on an object, there must be a constant acceleration. That acceleration will always be in the same direction as the unbalanced force. And if we have small net forces, we'll get small accelerations. If we have large forces, we'll get large accelerations. Newton took that idea and put it into his second law. His second law simply states that objects accelerate proportional to the net force, more acceleration, are inversely proportional to the mass of the object. Meaning if you increase the mass of an object, it will increase its inertia. It's going to try and keep doing what it was last doing even more. Heavy things at rest really want to stay at rest, and it takes a ton of force to actually accelerate them. Whereas light things don't have a lot of mass. They're at rest, but if you apply force to them, they'll quickly be put into motion. And the same thing is true for things in motion. Things that are big and heavy and in motion want to remain in motion, and things that are light can be taken out of motion very, very quickly. The units there for force, we've got metric units in terms of newtons. Since he's the one that did a lot with force, we name the unit after him. And it's a mass multiplied by an acceleration if you solve it out for force. If you want to go pounds, pounds is the unit of force that we're used to here in the States. Our mass then would be measured in something called slugs, and our acceleration would be in feet per second squared. If you were curious about how many slugs you are, just take your weight and divide it by the acceleration due to gravity, and that'll determine how many slugs of mass you are in an English unit. In this example here, we've got 2 cartons of ice cream, both being pulled with the same exact force. Because the stretch in the rubber band looks identical, the one with the smaller mass will accelerate faster. And here's a free body diagram of that ice cream. Only force I saw on it was the rubber bands, so one force applied to the right. If there's forces acting in more than one dimension, objects can accelerate in more than one dimension. Just keep all your vector components separate, keep all your i's, j's, and k's separate for each other, solve for the net force, and then object will accelerate in whatever direction the net force points.